here is another example. This is one of my favorite examples. This is one which looks easy at the beginning. It's just the integral of secant x. What could be difficult about it? Well, try all of the methods that you have at your disposal. You want to try substitution, integration by parts, identities, and so on. They're not going to work. But once again, please do try them. And you will learn something about why they're not going to work from each one of those methods. Okay? So what is going to work? Well, look at this thing. This is really neat because it really does not so much use trig identities as a little bit of thinking and observation. So standing back and trying to figure out, what do I know about this? Well, we're trying to figure out what the integral of secant x is, and we don't know how to do it, but we notice that the derivative of secant, as we remember, is secant times tangent. Okay, so the derivative of secant involves a tangent. Well, what about tangent itself? What is its derivative? Well, the derivative of tangent is secant squared, which I can write as secant times secant. Well, now look at those two formulae. Both of them have a factor of secant x, which is exactly what we're trying to integrate, and then the remaining factor is basically the original function but switched around. So the secant ends up being in the derivative of tangent, and the tangent ends up being in the derivative of secant. Okay, what we're going to do is we're going to take advantage of this fact, okay, and we're going to use an old trick that is multiplying and dividing. So what we're going to do, so we're going to start from our secant x, we're going to multiply and divide by the sum of secant plus tangent. Okay? So if you actually expand the top, that ends up looking like that, secant squared plus secant tangent. Well, as you can see, in the top we have the derivative of the bottom. And that suggests doing a change of variable, a substitution. We're going to let u equal secant plus tangent, and that's exactly what we have in the denominator, right? And what does the differential turn out to be? Well, once we compute it, of course, the derivative of secant is secant tangent, the derivative of tangent is secant squared, and look at that, even though with reverse order of the terms, but we end up with, in the differential, exactly what we have on top. So once we try to do the substitution, our integral becomes simply the integral of, well, the whole numerator times the x, that's all du. So we're just left with the 1 on top, and the denominator is our u. So that's just the integral of 1 over u du, which we know to be the logarithm of the absolute value of u. And now all we have to do is switch back to secant plus tangent, and here you have it. Would you have guessed that this was going to be the antiderivative for secant x? Not very easy, not intuitively. But again, just you may want to go through the procedure and look at how smart the observation is about the relationship between secant and tangent, and how that gives us the right method to do it.